Hey everyone, just thought I'd make a little quick video over section 4.7. So I'm going to go through at least a few of the examples in here just to give you a good idea of how to actually solve these optimization problems. So I think I go through about half of the actual notes, but I'm just going to show you the answers. I'm going to walk you through it. So this is the little before class stuff. It says rather than go straight into optimization, we'll give some motivation for the process first, as well as to connect it to material we've already learned. So it says consider the function f of x is minus x squared plus 6x plus 11. It says find the critical point of f of x. Give your answer as an ordered pair. So remember, the critical points are the points wherever the first derivative is equal to 0. So first thing I need to do is find the first derivative, f prime of x. And if I do that, f prime of x is minus 2x plus 6. And then I can set that equal to 0 and solve, and it's equal to 0 when 2x is equal to 6. So that implies that x is equal to 3. So that's my critical number. Now I want to find the y-coordinate whenever I have x is 3. So all I do is plug x is 3 back into the f of x. And when I do that, I get 20. So now I have my critical point of f of x is the ordered pair 3, 20. So now the next step was to kind of visualize this. So we want to sketch the graph of f of x to visually confirm your answer. So I just kind of give a rough sketch. I didn't copy and paste a graph in Desmos like I should have, but it gives you the same idea here at the maximum is at 320. And that's where the critical point occurs, right? That's where the first derivative is equal to 0 at a local max or a local min. So now it has this other idea. It says, now suppose that f of x gives the profit in hundreds of dollars that a company makes from a certain product when X thousand units are sold. The critical point found in part A then has a meaning, and it's given by this. Whenever we sell 3,000 units, the company reaches its maximum profit of $2,000. Because X is measured in thousands of units, so that means 3,000 units are sold, and Y is measured in hundreds of dollars, so 20 times 100 is $2,000. So that's just the motivation behind this. So now it actually goes into a real example. So it says a farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field with the largest area? So what I did here was I drew a little bit of a kind of a figure to kind of illustrate this. So here on the left-hand side in the blue, we have the river, and on the right-hand side in the black, we have the fencing, and there's no W along the river right here on this part. So there's no W right here because it says we don't need fencing along the river. So that's why I just have an L up top and bottom and then a W on the side. So I can figure out two different things from this. So it says I have 2,400 feet of fencing. So that means the perimeter, when I take L plus W, that would be 2,400 feet. So that would be 2L plus W is 2,400, or I can solve that equation for W and get 2,400 minus 2L. So now the next equation I can create is in terms of the area, because that's what we want. We want what are the dimensions of the field with the largest area. So we need an equation for the area of this field right here. So what we're going to do is take the area is equal to the length times the width. But up here, we already have the width in terms of the length. So what we're going to do is substitute that in here, right? So whenever we do that, we end up with the area is equal to 2,400 L minus 2L squared. Now back from section 4.5, we know that whenever we're trying to maximize or minimize something, usually what we want to do is take the derivative and set it equal to 0 and solve the equation, right? So here, I take the first derivative of A. So when I do that, I take the derivative of 2,400 L, that's 2,400. And then derivative of negative 2L squared is negative 4L. And then I set that equal to 0 and solve. So whenever I set this equal to 0 right here, this happens whenever 4L is equal to 2,400. And I can just divide both sides by 4 to solve for L, and L is 600. So now we know what the length of the field should be. Now what we want to do is actually figure out what the width is. So what we do is take our length that we just solved for, plug it back up in here and solve for W, and that we would take 2400 minus 2 times 600, or that's 2400 minus 1200, and that's 1200. So now we know what L is, we know what W is. Now we need to indeed check that this is a maximum, so we need to take the second derivative. So when we take the second derivative of A, we get this is equal to -4, and -4 is less than 0. So since the second derivative is negative, that means we have a function that is concave down, and since it's concave down, it indeed does have a maximum. So thus, L equals 600 feet and W equals 1200 feet does indeed maximize the area. So that's kind of the idea. We have one equation, and we're going to solve that one equation in terms of the other variable, and then we're going to plug it into another equation, and then maximize that function by taking the derivative and set it equaling to 0 and solving. So that's what this idea for strategy behind optimization is. So the first step is you introduce all the variables, if applicable, draw a figure, and label all the variables. Then we determine which quantity is to be maximized or minimized. Write a formula for the quantity to be maximized or minimized in terms of all the variables. And then the fourth step, we want to rewrite the function to be maximized or minimized in terms of just one variable. And then once we've done that, we want to locate the maximum or minimum value from the fourth step. So that involves taking the derivative, setting it equaling to 0, and solving it. And if we're dealing with a particular interval value, then we want to evaluate it at the endpoints as well, just like how we did in section 4.5. So the key to these optimization problems is just practice. Many optimization problems follow a similar pattern and require only slight modifications from other problems. Practice is the only way that you will learn and recognize these patterns. So let's look at example 4.7.3, and it says a cylindrical can is to hold a volume of 1 liter of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So let's think of it this way. So first, we're given a volume in the question. So we know that we're going to have a volume. So we know what the volume of a cylinder is. It's pi r squared h. But we already know what the volume that the can holds is. It's 1 liter. So what I want to do is take this equation here for the volume, and I want to solve this for h in terms of r. So if I do that, I just divide it over, and I get that the height is equal to 1 over pi r squared. So now, the second thing you need to figure out is, so we want to minimize the cost of the metal to manufacture the can. So that's equivalent to minimizing the actual surface area that the can takes up. So I need to figure out what the surface area for a can is, for a cylindrical can. So it's actually equal to, it's given right here, 2 pi rh plus 2 pi r squared. But I already know what h is in terms of r. So I can take this expression here and plug it in right here for h, right? So that's what I did. And then I simplified. So once I do the simplification, I end up with 2 over r plus 2 pi r squared. So now that's my equation for the surface area, right? So now I want to take the derivative of that and set it equal to 0 and solve. So when I take the derivative of this equation right here, 2 over r plus 2 pi r squared, I get -2 over r squared plus 4 pi r, and when I set that equal to 0, that happens when 2 over r squared is equal to 4 pi r, and then I just solve for r, and I get that r is the cubed root of 1 over 2 pi, or 0.542. So now I know what r is. R is 0.542. Now I can solve for h because up here I have h in terms of r, right? So just plugging that back in up there, I can solve for h and get that h is approximately 1.084. So now I know what r is at 0.542. I know what h is at 1.084. Now what I want to do is check the second derivative. So if I check the second derivative, I'm taking the derivative of this function here, right? The derivative of the first derivative is the second derivative, and when I do that, I get 4 over r cubed plus 4 pi. And this is positive because r must be positive, so r cubed is positive. So that means 4 over r cubed plus 4 pi is positive. And since the function is positive, that means we have that the graph is concave up and it does have a minimum. So that implies that r equaling 0.542 and h equaling 1.084 will minimize the cost to manufacture the can. So that one wasn't too bad. We had to use two equations, right? One for the volume, one for the surface area. We had to figure out which one we wanted to minimize in this case. So we wanted to minimize the surface area equation. So we wrote the surface area as a function of one variable alone, in particular, the radius. Then we took the derivative, set it equal to 0, and solved for r. And once we knew what r was, we could find out what h is by plugging it back into the expression for h. So now, let's go on to the next one here. It says find the point on the parabola y squared equals 2x that is closest to the point 1,4. So I gave you a little picture right here. So the point 1,4 is right here. And then that orange distance there is the vertical distance from the point 1,4 to the parabola y squared equals 2x. So we want to minimize the distance, right? So the vertical distance, think of it this way. We can just use the distance formula, right? If we want to know what the distance from some point to 1,4 is, we can use the distance formula and get that it's equal to the square root of x minus 1 squared plus y minus 4 squared. But we also know that the parabola has the form y squared equals 2x, right? So I can solve for x in terms of y by just dividing both sides by 2, and I get that x is equal to y squared over 2. Then I want to plug this right here, the x equals y squared over 2, back into the formula D, right? So I just plug it back in here. And what I want to do now is it's actually going to be easier to minimize the distance squared instead of the distance because this original distance formula involves a square root, right? So what I did was I squared both sides of the equation and then they expanded. So when I do that, I get that the distance squared is equal to y to the 4th over 4 minus 8y plus 17. And now if I want to minimize this, all I do is take the first derivative and set it equal to 0. When I take the derivative of y to the 4th over 4, I get y cubed. When I take the derivative of negative 8y, I get negative 8. When I take the derivative of 17, I get 0. So this second derivative equals 0 when y equals 2. All I do would be move the 8 over here and then take the cubed root. And if I do that, I get y is 2. Now, what I want to do is solve for x. So I know that x is equal to y squared over 2, so all I do is plug y equals 2 into that expression there and solve for x, and I get that x is. Now what I want to do is, again, check the second derivative. So the second derivative is the derivative of this function here, so that would be 3y squared. And again, particularly, this is positive because y squared is always positive. So this is a concave up function, and it has a minimum. So now, this implies that the closest point on the parabola to the point 1,4 is the point 2,2. So those are just a couple of ones to get you warmed up. Now let's go into the pre-class practice problems. So these first couple ones aren't too difficult. So it says find two numbers whose difference is 150 and whose product is a minimum. So what we want to do first is define these two numbers. So I say let x be the first number and let x plus 150 be the second, because these are two numbers that easily their difference is 150. Now, what we want to do is first define their product, right? Their product is found by just multiplying the two numbers, right? X times x plus 150. And if I multiply that out, it's x squared plus 150x, right? Now, to minimize this, again, we're going to take the derivative and set it equal to 0 and solve. So when I take the derivative of x squared plus 150x, the derivative of x squared is 2x. The derivative of 150x is 150. So And then I set it equal to 0 and solve. And this happens when 2x equals negative 150. And then dividing both sides by 2, I have that x is equal to negative 75. So now I know what this first number x is here. It's negative 75. So I can solve for x plus 150 by just taking negative 75 and adding 150 to that. And if I do that, it equals 75, right? So now I know the two numbers, negative 75 and 75. Now I need to check that they actually minimize the product. So I need to take the second derivative of the product. So I'm going to take the derivative of this part here, 2x plus 150. When I do that, I just get the second derivative is 2. And 2 is positive, which implies that the function is concave up and it has a minimum. So thus, the two numbers that give us a difference of 150 and minimize the product are negative 75 and 75. So now let's move on to the next one. The next one says the sum of two positive numbers is 20. What is the smallest possible value of their sum of squares? So the first piece I know, their sum is 20. So that means I have two numbers, x plus y, that sum to 20, right? So, and what I want to do is minimize their sum of squares. So I want to minimize x squared plus y. So what I first did was I rewrote this top equation here, where I just have y in terms of x, right? When I do that, y equals 20 minus x, and then I plug this y back up here into the sum of squares. So when I do that, I write out the expression for the sum of squares, and if I simplify it, I get that 2x squared minus 40x plus 400 is the formula for the sum of squares in terms of x. So now to minimize this again, we take the derivative and set it equal to 0. When I take the derivative of this right here, the derivative of 2x squared is 4x. The derivative of negative 40x is negative 40. And the derivative of 400 is 0. So now I set this equal to 0 and I solve. And if I do that, this would be when 4x equals 40 or when x equals 10. So I know that x equals 10 now. So now I can solve for y, right? Because up here I have y in terms of x. So I can solve for y and I get that y is 20 minus 10 or it's 10. So x and y are both 10. Now we check the second derivative again. So we're going to take the derivative of this function here. So when I take that derivative, it's equal to 4. And in particular, 4 is positive, so that implies that the function is concave up and it has a minimum. So therefore, we do have the smallest possible value, the sum of squares. And this happens whenever we have the two numbers are x is 10 and the other number is 10 as well. So now let's move on to example 4.7.7. So here for example 4.7.7, it says, what is the maximum vertical distance between the line y equals x plus 2 and the parabola y equals x squared for x being in between negative 1 and 2? So what we want to do is, so the vertical distance between these two, y equals x plus 2 and y equals x squared. So we can just take the difference between this here and this here, right? So this would be x plus 2 minus x squared. And whenever I do that, I just get the equation x plus 2 minus x squared for the vertical distance between the two. So now I want to maximize this, so we take the first derivative and set it equal to 0. When I take the derivative of this function here, I end up getting 1 minus 2x. I set that equal to 0 and solve. And this would happen when 2x equals 1 or when x equals a half. So now, this is where we have to think a little more, because this is on just the interval minus 1 to 2. So what we need to do is evaluate the actual distance at the endpoints negative 1 and 2, and we also need to evaluate it at the critical point x equals a half. So that's what I did here. I found the distance at the point minus 1, and if I do that, it's 0. Then when I find the distance at the point x equals a half, it's 2.25. And then when I find the distance at the point 2, it's 0. So again, here we have that this actual maximum distance occurs when I have x equals a half, and the actual value of the maximum vertical distance is 2.25. So that's how we solve that problem there. All we were looking for is the maximum vertical distance. So we could check that this actually is a maximum by saying, what's the derivative here? So the derivative of 1 minus 2x is negative 2. And negative 2 is less than 0, so that implies that it is concave down and it has a maximum. So now, those are all the pre-class exercises. Now let's go to the end-class ones that are a little bit more tricky. So what I did was I actually drew out a couple of pictures for a couple of these to solve. So it says a woman launches her boat from point A on a bank of a straight river 3 miles wide and wants to reach point B that's 8 miles downstream on the opposite bank as quickly as possible. She could row her boat directly across the river to point C and run to point B, or row directly to point B and then row directly to B. So we would go A to C and then run from C to B. Or what we could do is row from A to some intermediate point D and then run to B. So what we're going to have to do here, this one's a little tricky, so I'd give a picture here. So here we know that the distance from A to B is 8 miles downstream, but B is on the opposite bank, so B is right here. And we know that the distance between this point over here that's right across from A, which is C, the distance between C and B is 8. So now what we need to figure out is a couple of different things. We need to figure out what the actual total time we're going to have is, because we want to minimize the time we spend getting to point B. So here what I did was first let this distance here from A to where we have the point across from D, let this distance here be x. And what I want to solve for is this distance here, the rowing distance from A to D. So the rowing distance from A to D, we can find that, right? So this is a right triangle right here. So I can find the distance from A to D. So here this distance of this side is x. Here this distance is 3. So by the Pythagorean theorem, this distance A to D is the square root of x squared plus 3 squared, right? So that's this numerator here. This is the distance that we're going to travel, the square root of x squared plus 3 squared. And now if I want to know what the actual rowing time is, I know how fast she can row. She can row at 5 miles an hour. So this implies that the actual rowing time can be found by the distance traveled divided by the speed she can row. So that is our rowing time. Our rowing time is equal to the square root of x squared plus 9 over 5. Now we can actually find the actual running time. So if she has traveled this distance here to point D, then I know that the actual running distance she has, which is if I look at this side here, this distance here is 8 minus x, right? So the only running time she has left, or the only running distance she has left, pardon me, is 8 minus x. And then if I want to find the time that she's going to spend running, I take that distance of 8 minus x and divide it by 6. So now I have the rowing time. I have the running. I can find the total time that she's going to spend, right? So all I do is take not the difference, but the addition between the running time and the rowing time. And if I do that, I get this total time right here. Now, remember, I want to minimize this total time, so I'm going to take the derivative with respect to x. And if I do that, it ends up being right here. So this part here, you have by 10 times x squared plus 9 in the denominator, and then minus 1/6. Now I can first I want to move the 1/6 over here, right? Now what I can do is cross multiply. And if I do that, I get 6x equals 5 times x squared plus 9 under the square root. Now I can square both sides. And once I square both sides, I'll get rid of that square root. And I'll arrive at 36x squared equals 25x squared plus 225. Now I can subtract this 25x squared to this side, and I'll get 11x squared equals 225. And then I can divide both sides by 11 and then take the square root and get that x is equal to the square root of 225 over 11. And if I do that decimal approximation, its x is approximately 4.52. So now I need to check the second derivative again, and if I do that, it's positive. And in particular, it's concave up, and that applies we actually have a minimum. Now, this means that to reach the point D as quickly as possible, what we need to do is land 4.52 miles downstream from point A. All right, so now on to example 4.7.9. So this says, find the largest area or the largest rectangle which can be inscribed in a semicircle of radius r. So what I did first is I drew a semicircle over there, it's in blue, and I drew a rectangle inside of it. So what we want to do is see what is the area of the largest rectangle we can put in there. So first thing we need to do is define the formula for the top of a semicircle. So it's actually simply, if you go back to the equation of, remember a circle has x squared plus y squared is r squared, right? So all I did here was I solved for y, and I just took the positive square root. That's what I did to solve that for the top portion of the semicircle. And the area of a rectangle, we know the formula for the area of a rectangle, right? It's length times width. So I needed to figure out what was the length of the rectangle, what was the width. Here's the length. It was x plus x, or 2x. The width was y. So now, here, based on my formula for the semicircle, I have y in terms of x. And we can think of this r here as just a constant. Just think of r as a constant. So then we plug this expression for y into the area formula, and we get it's equal to 2x times the square root of r squared minus x squared. Now, again, to maximize this area, we want to take the derivative and set it equal to 0. So in this case, it involves the product rule. We take the first times the derivative of the second, which will end up giving you a 2x times a minus x over r squared minus x squared under the square root. And then we do plus the derivative of the first times the second. And that'll give us the 2 times the square root of r squared minus x squared. So now what we can do is write this all over a common denominator of the square root of r squared minus x squared. And how do we do that? We just multiply this term here by the square root of r squared minus x squared, and it will give you 2 times r squared minus x squared minus this 2x squared piece over here that we get. From the 2x times negative x gives us the negative 2x squared. So now we set this equal to 0, and we solve it. So when we set this equal to 0, this happens when just the numerator is equal to 0, right? So when 2r squared minus 2x squared equals 2x squared, I add the 2x squared over, I get 4x squared equals 2r squared. I solve for r, and I end up getting that x is equal to the square root of r squared over 2. But I can actually simplify that because the square root of r squared is r. So I'm left with r over the square root of 2 for x. So now I know what x is. It's r over the square root of 2. I know how I can find y using this equation here. So all I do is plug it back in, right? So then I have y is equal to the square root of r squared minus r over the square root of 2 squared. So this is r squared minus r squared over 2. And this is just r squared over 2 again. And then when I take the square root again, I get r over the square root of 2. So now I know what y is y is r over the square root of 2. I know what x is. So that means the maximum area, which we can find by 2x times y, is 2 times r over the square root of 2 times r over the square root of 2. So the square roots of 2 become 2, and then I take r times r becomes r squared. So I have 2r squared over 2, which is just r squared. So r squared is the largest area of a rectangle that we can inscribe in the top of a semicircle or on the bottom of a semicircle. Either way, it works. So now let's move on to example 4.7.10. So both of these here kind of have the similar idea of trying to minimize the amount of material that is used or minimize the cost. So let's just go over example 4.7.10 real quick. So it says a box with square base and open top must have a volume of 32,000 cubic meters. Find the dimension of the box that will minimize the amount of material used. So we know what the total volume is. So what I first did was I created this box over here. I took a picture from the internet, copied and pasted it in, and labeled it. So it has a square base. So the sides right here and here are the same. And we'd have a different height, right? So I can find the volume by taking the length times the length times the width, because the length and the width are the same. So that's why it says the length times the height. So, and that equals L squared H, right? But we know that the volume is equal to 32,000 already. It was given. It was 32,000 cubic centimeters. So solving for H here, I can get that H is 32,000 divided by L squared. So now, so we have H in terms of L. So now, to minimize the material we actually use, we minimize the surface area that it would take up. So all I did was I found out what's the total surface area. So if I do that, there are 4 of these sides of this thing, right? So we have L times L, right? Or L times H, excuse me. We have 4 of these, 1 here, and then 2 on the opposite sides. So then we have that the surface area is equal to 4 times LH, which is this right here, L times H, and there's 4 of them. And then we have L squared, which is the square base. So now we can multiply that out. But first, what we want to do is plug in our expression for H in terms of L. And if we do that, we end up getting the surface area is equal to 128,000 divided by L plus L squared. So now we have a formula for the surface area in terms of L alone. So now what we want to do is, again, take the derivative and set it equal to 0. Here it uses the power rule in both places. The derivative of 128,000 over L is minus 128,000 over L squared. The derivative of L squared is 2L. We set it equal to 0 and solve. So here we have 2L equals 128,000 over L squared. I multiply both sides by L squared to get 2L cubed equals 128,000. I divide by 2 to get L cubed is 64,000. Then I take the cubed root to get L is 40. So now I know what L is. So now I know what L is, I can go back up here and find out what H is, right? So I just plug L in up there for that expression. And then I have that H is equal to 32,000 over 40 squared. So this is 32,000 over 1,600, which is just 20. So now I know what L is. L is 40. I know what H is. H is 20. Now I need to check the derivative. So checking the second derivative, I get that the second derivative is 256,000 over L cubed plus 2. So in particular, L is positive. So this part here must be positive. So something positive plus 2 is positive. So that implies that the function is concave up and that it has a minimum. Thus, L equals 40 and W equals 20 minimize the material. If we want to talk about units here, this would be 40 centimeters and 20 centimeters because the volume is in cubic centimeters, so the original units must be in centimeters. So the last example I'm going to go over in here is example 4.7.11. This one's pretty similar to the last one. So it says a rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of its base is twice its width. So what I did here is that this length here is equal to twice the width W, equal to 2W. So that's why it said that length right there is 2W. It says material for the base costs $10 per square meter. Materials for the sides cost $6 per square meter. So the square base is this piece here. Or the base is this piece here, right? So we know what the volume is, right? The volume is equal to 10 cubic meters. And since this is a rectangular storage container, we know what the volume formula is. It's length times width times height. But we know that the length already is equal to 2W. So I plug that in. And I also know the volume already. It's 10 cubic meters. So therefore, I can solve for H in terms of W. And if I do that, H equals 5 over W squared. So now what we want to do is figure out the cost equations, right? Because we want to find the cost of materials for the cheapest container. So we want to minimize the cost. So this is what we need to actually express in terms of one variable alone. So I know that the base portion costs $10 per square meter, and I know that the area that I can find is equal to 2W times W, right? That'll give me the area of the base. 2W times W is 2W squared, and then times the cost, which is 10. So we get the cost for the base is 20W squared. Now, we have to figure out how much the sides are going to cost. We know what the base is going to cost. What's the sides going to cost? So we need to first say that the sides cost 6, right? And we know that each side has 2WH, and we need to multiply that by 2 to take into account both sides. So when we do that, we end up with here 24WH, but H we had in terms of W, so we can actually do that first, and that'll give us 120 over H. So think of it this way. Two of these are going to have a certain size where we have 2W and H. So this side here and the side on the opposite one that mirrors it, right? They're going to have 2W times H, and we have two of them, right? While this other one here is just this side here, and the one on the other side that mirrors it would be just H times W. That's why here we have 2WH times 2 and WH times 2, because there are two different areas on each of the sides, depending on whether we're looking at 2W as the length or here we have W. So when we do that, we end up with the total cost for the sides. Here we have 120 over W plus 60 over W. That's 180 over W. So we have 180 over W for the sides, plus the cost of the base is 20W squared. So now, again, to minimize this cost, we take the derivative and set it equal to 0. So whenever I do that, this is when 40W minus 180 over W squared equals 0. So all I do is move the 180 over W squared over to the left. So whenever we have 40W equals 180 over W squared, then we multiply both sides by W squared to get 40W cubed is 180. We divide both sides by 40, and we get that first. 180 over 40 is this 4.5, but then I have to take the cubed root because it's W cubed. So this implies that W is equal to the cubed root of 4.5. Now, I know what the length is, right? The length says it was equal to twice the width. So it's just the length is 2 times the cubed root of 4.5. So now I know what W is. I know what L is. I can solve for H, right? H is up here. Oops, let's go back. H is right here. So all I do is plug in W into there. And when I do that, I end up with 5 divided by 4.5 to the 2/3 power, right? Because what we're doing here is we're taking this and we're also squaring it, right? Because we have W squared here. So what we're doing is it's 5 over 4.5, the cubed root of 4.5 squared, which I can also write as 4.5 to the 2/3. So now we know what W is, we know what L is, we know what H is. Now we just check the second derivative again. And if we do that, it's 40 plus 360 over W cubed. In particular, this part must be positive, and something positive plus 40 is already positive. So this implies the second derivative is positive, and the function is concave up, so it has a minimum. So therefore, L equals 2 times the cubed root of 4.5, W equals the cubed root of 4.5, and W equals 5 over 4.5 to the 2/3 will actually minimize the cost. And that's all that I'm going to cover over in this video for section 4.7.